double-click Visual FEA icon to start the program. Select New Item from the File menu. Then, Project Setup dialog pops up for the setup of a new project. The dialog has a number of items related to analysis types and procedures. In this screen demo, only plane strain radio button is turned on for a linear static analysis of plane strain case. Click OK button to complete the project setup. The first step of the finite element analysis is to create the mesh representing the geometry of the analysis model. In this example, a two-dimensional plane mesh is to be generated in a region bounded by a number of connected curves. In order to create a circle or circular arc, press the Circular Arc button. Input the center of the circular arc by clicking a point on the XY grid plane. Make a circular arc by designating its starting point and then ending point. Switch the Tool button to the Straight Line tool. A straight line is created by clicking the starting point and the ending point consecutively. 3 more lines are created to complete the boundary lines of the region. The next step is to generate a planar mesh over the region bounded by the curves. The density of the mesh is determined by the division of the boundary curves. In this example, the 2 lines bounding the top and right sides are divided into 8, respectively. First, press the Curve Selection button. Select the lines and choose Divide 8 item from Divide menu. The circular arc is divided into 10. Select the arc and choose Divide 10 item from Divide menu. The other 2 straight lines will be divided so that the mesh density is gradually varied from dense near the circular arc to coarse outwardly. Thus, select the lines and apply Divide Smart of Divide menu. Now, the planar region is ready for mesh generation. Choose Auto Mesh item from Mesh menu. Auto Mesh dialog pops up, and at the same time, the region selection button is pressed automatically. If you move the mouse and place the cursor over the region, then you will find the region is highlighted in green color. Click the mouse button to select the region. Press the Generate button of Auto Mesh dialog. Alternatively, double-clicking will also generate the mesh. The mesh generation filled the region with 3-node triangular elements, because the option of element type is set to triangle only. Let's test another case with 4-node quadrilateral elements. Select Undo from Edit menu. The triangular mesh is removed. Set the element type option to quad only. Move the cursor over the region. Then, the region is highlighted in green. Select the region by the left mouse button. Click. Double-click the region to generate a planar mesh with 4-node quadrilateral elements. The next step is to assign the element property to the mesh. Choose Element Property item from Assign menu. Property dialog pops up, and Mesh Selection tool is automatically pressed. The initial setting of the dialog shows that the element type is plane and the elasticity type is linear elastic. The element type and elasticity type can be set as desired, using the drop-down list box. As you move the cursor over the input items, there appears a yellow tooltip with a short description about the item, such as modulus of elasticity, or Poisson's ratio. Change the value of input items if necessary. Select the mesh by clicking it. The mesh color turns into blue. Press Assign button to assign the property set of the dialog to the selected mesh. In order to assign the boundary conditions of the model, first select Boundary Condition item of the Assign menu. The Boundary Condition dialog appears on the screen, and the Curve Selection tool is automatically pressed. The dialog has the items specifying the constraints of the displacements. Here, delta x implies the constraint of the displacement in the x direction. If this item is checked, the displacement in the x direction is constrained. Delta y implies the constraint of the displacement in the y direction. If this item is checked, the displacement in the y direction is constrained. Now, The delta y item is unchecked by clicking the box. Thus, this set of boundary conditions specifies the displacement constraint in the x direction and free movement in the y direction. Select the left side line and press Assign button. So, this side is constrained as a roller moving only in the y direction. Click New button of the dialog to create a new set of boundary condition. In the new set, release the constraint in the x direction, and constrain the movement in the y direction. Select the bottom line and press Assign button. So, the bottom of the model is constrained as a roller moving only in the x direction. In order to assign the load condition, select Load Condition item from Assign menu. Load Condition dialog pops up. The dialog has a drop-down list with various types of load conditions. Select the type of load condition from the drop-down list box. As the type of the load condition is chosen, the Relevant Selection tool is activated automatically. For example, if you select Nodal Load from the drop-down list, the Node Selection tool will be activated. In this screen demo, Uniformly Distributed Load is selected, and accordingly the Curve Selection tool is activated. It is because uniformly distributed loads can only be assigned to boundary curves in a plane strain model. Change the intensity of the load to 10. Select the right side line, and click Assign button. Then, the uniform load is applied along the side line. Select the Arrow Off Object item from the Assign menu. This action changes only the display of the load condition, but not the attributes of the load condition. Once the model is completely created, the next stage is to solve the problem represented by the model. Choose the Solve item from Solve menu. Then, the Analysis option dialog appears on the screen. Visual FEA supports 3 different solvers, namely, Frontal, Skyline and Sparse Solver. Each of the solvers produces exactly the same results, but they are different in the computing time and memory space required for the equation solving process. In this example, Skyline Solver is used. Click OK button. Then, the File Save dialog appears. Input the name of the file. And click Save button. Then the File Save dialog closes, and the solution process goes on. The equation solving process is completed within a second for this simple example. Solving equations produces huge quantity of data. The data can be visualized in diverse forms by the items in Post-Pro menu. The most frequently used form is the image of contours. In order to obtain the image, choose Contour item from Post-Pro menu. Contour Display option dialog has a drop-down list of data items which can be selected for display. Let's take an example of displaying the contours of the normal stress in x direction. Click OK button. Then, the stress contour image is displayed. A specific level of stress contour can be identified by clicking and dragging the cursor point. The image can be moved to a desired position by dragging with the right mouse button pressed. Now, the state of stresses can be figured by a Mohr circle. Select Mohr circle item from the Post-Pro menu. Then, Mohr circle diagram window opens. The Mohr circle diagram will be drawn on the lower part of the window, and there are a number of items for display options on the upper part. If you click a point on the stress image, there appears a small square, namely the stress square. Each edge of the square is attached with a pair of arrow symbols representing the normal stress and shear stress respectively. At the same time, the diagram window shows a Mohr circle representing the state of stresses at the center of the square. The horizontal axis of the diagram is sigma, n-axis, with the coordinate of normal stress, and the vertical axis is tau-axis with the coordinates of shear stress. The blue and red lines of circle diameter correspond to the directions of the normal stresses. Currently, the blue line corresponds to the x-axis, because the normal stress in the x direction, sigma x, is selected. The red line corresponds to the y-axis, orthogonal to the x-axis. The stress square can be dragged to any position over the contour image. The Mohr's circle diagram is updated instantly to reflect the stresses at the moved position of the square. The diagram can be resized using the scale trackbar. And the diagram can be moved to a desired position by dragging. There are 3 different methods of changing the stress direction. The first method is to use the angle trackbar. Slide the pointer of the trackbar. Then, the direction angle changes and the stress square rotates. At the same time, the blue and red lines of the Mohr's circle diagram also rotate. Press the Update Contour by Rotation checkbox here. Then, in accordance with the angle change, the stress contour image is refreshed instantly to show the normal stresses in the rotated direction. The second method of changing the direction angle is to drag the end of the diameter line. Place the cursor over one end of the lines. Then, the cursor turns into finger shape. Press the mouse button and rotate the line by dragging. The third method is to rotate the stress square. Place the curve over an arrow, representing a normal force of the stress square. The cursor turns into finger shape. Press the mouse button and rotate the square by dragging the arrow end. The diameter of the Mohr's circle are relevant to the 2 perpendicular directions formed by the rotated stress square. Place the cursor at one end of the diameter drawn in blue color. Then, the point is marked with a small circle, and a blue tip box pops up nearby. The tip box displays the coordinates of the marked point in sigma n and tau space. The angle theta shown in the tip box is equivalent to the angle between one of the perpendicular directions and the x-axis. The point of the Mohr's circle corresponds to an inclined plane, whose normal direction makes angle theta with the x-axis. In order to show this relationship, the square turns into a trapezoid with an inclined edge representing the inclined plane. 2 arrows on the edge indicate the normal and shear stresses developed on the inclined plane. Place the cursor at the end of the red line. The blue tip box pops up again. This time, the point of the Mohr's circle corresponds to a complementary plane, perpendicular to the previously inspected plane. The square turns into a trapezoid with an inclined edge representing the complementary plane. The tip box shows the information about the complementary normal and shear stresses developed on the complementary plane. Whenever the cursor is placed over any point of the Mohr's circle, there appears a yellow tip box with the information about the state of the stresses on the relevant plane. And a white line is drawn connecting the point to the center of the circle. This white line corresponds to the inclined plane represented by the trapezoid displayed over the stress contour image. It is shown that the angle between the white line and x-axis is 2 theta. The numerical figures in parentheses denotes the Mohr circle coordinates in sigma n and tau space. Placing the cursor over the text pops up a purple tip box with the formula, calculating the normal stress, sigma n, and shear stress, tau. Let's move the cursor to the numerical texts on the other side of the Mohr circle. This time, the tip box shows the formula for complementary normal stress, sigma n prime, and complementary shear stress, tau prime. There are a number of control items related to the Mohr's circle diagram. The display controls can be used to make the diagram either simple or distinguishing. The captions and notations of the diagram can be turned on or off selectively. Check or uncheck the items shown here. Sigma x, sigma y, and tau xy represent the normal and shear stresses. Sigma 1, Sigma 2 represent the principal stresses. Theta notations denote the direction angles of normal stresses. The numerical figures in parentheses are the coordinates of Mohr's circle point. The x and y axis are perpendicular in Cartesian coordinates, but laid straight in the Mohr's circle diagram. There are additional display options for control of the diagram. Failure envelope is used only in elastoplastic analysis, and thus, this item is disabled for the current case of linear analysis. The red line of circle diameter is related to the complementary stresses, and can be turned on, or off. In the current case of plane strain analysis, there exists a stress component in the z direction normal to the plane. That is sigma z. The Mohr's circle diagram consists of 3 circles, if sigma z is included. The original circle represents the stresses in the xy plane. 2 extra circles in white color represent the stresses in the yz plane, and zx plane, respectively. The Mohr circle diagram is drawn with negative sign for compressive stresses. Checking this box reverses the sign, and thus, flips the diagram horizontally. We have observed the case of the inclined plane with the rotated stress square. In this case, the sigma n button is pressed. In order to return to the initial state, press the sigma x button. Then, the square is reset to the initial state with a normal direction parallel to the x-axis. The contour image shows the normal stress in x direction, sigma x. The blue line of the Mohr's circle is aligned to the x-axis. The tip box shows that the normal stress is equal to sigma x and the shear stress is equal to tau xy. Press the sigma y button. The contour image shows sigma y, and the blue line is aligned to the y-axis. The tip box shows that the normal stress is equal to sigma y and the shear stress is equal to tau yx. Press the sigma 1 button. Then, the contour image shows the maximum principal stress. The square rotates to indicate the sigma 1 direction at its center. It is shown that the sigma 1 and sigma 2 directions can be drawn directly on the Mohr's circle diagram. The tip box shows the formulas for sigma 1 and 0 shear stress. When the cursor is positioned on the numerical figures of the principal direction angle, theta 1, there appears a tip box with the formula for the principal direction angle. Pressing the sigma 2 button makes the blue line aligned to the minus sigma n axis. The contour image shows the minimum principal stress. The tip box shows the formulas for sigma 2 and 0 shear stress. The tau max button is used to display the maximum shear stress image and corresponding Mohr's circle diagram. The tip box shows that the normal stress is equivalent to the average of the sigma x and sigma y, and the formula for maximum shear stress. Lastly, the size of the stress square can be adjusted using the drop-down list. This is the end of the screen demo. The next demo will show how the Mohr's circle can be applied to an elastoplastic analysis.